we're going to look at the limit of sine of x over x as x goes to 0. Now there are a couple of ways to look at this. We are going to be looking at this kind of in a visual way. We're going to use the unit circle to visualize what's happening with sine of x over x. And we're going to try and squish it between two other values. So let's get the unit circle. And let's just go ahead and draw an angle x. Now remember, we're thinking about this x as it approaches 0. So let's go ahead and make an angle x. Now the radius of our circle, remember, is 1. Let's go ahead and play with this circle a little bit and see if we can get something that looks like our sine of x over x. So let's go ahead and draw a triangle. And we can draw another triangle as well. We'll just use this outside line here and go ahead and extend that to create a different triangle. This is a nice blue triangle. And the blue triangle also includes the area of the green triangle. We also have the sector. We can find the area of that sector right here. Let's go ahead and color that yellow. And this sector of the circle also includes that area of the green triangle. But now we can see we've got a center, something in the middle. That sector is in between the areas of the green triangle and the blue triangle. And let's go ahead and calculate the areas of those and see if we can kind of squish them together. So we know the area of a triangle is 1/2 base times height. Let's go ahead and find the area of the green triangle first. The area of the green triangle is 1/2 base. Now the base here, since it's a unit circle, the base is actually 1. And then times the height. Now the height is a little trickier, so let's go ahead and look at our angle x, and we have to remember our trigonometric functions. So if we look at the height right here, we know our height is just this section right down here. And we can write that as a trigonometric function. We know that the sine of x equals the opposite over the hypotenuse. The hypotenuse is 1. It's a unit circle. So sine of x equals the height. So we can substitute that in. Now the area of this green triangle is less than all of the other areas. So we can make an inequality here with 1/2 sine x less than the area of both the sector and the blue triangle. Let's take a look at the area of the sector. I'm just going to redraw it down here just so you can see it a little bit better. Now remember, when we have a section of the circle, we're really taking a fraction of the area of the whole circle. If we were to try and find the area of the whole circle, it would be pi r squared. Our r is 1. It's a unit circle. So that leaves us with the area of pi. Now we don't want the area of the whole circle because we just want that little section, that fraction, if you will. Now the whole circle has 2 pi radians, but we only want x of those. So our fraction that we're going to use is x over 2 pi. And that's the fraction of the area. So x over 2 pi times pi. Now pi and pi will cancel, and we have x over 2 as the area of our sector. Now let's go ahead and look at the area of the blue triangle, which is obviously greater than our sector right here. And again, we'll use the formula 1/2 base times height. So if we look at our base, it's again 1. Let's go ahead and color this all so we can kind of see the triangle that we're looking at. So 1/2 base, which my base is 1, times the height. Now let's use our trigonometric functions again to look at the height of this triangle. Well, we don't know the hypotenuse. The hypotenuse is a little bit longer than 1, but we do know the side that's adjacent, this side right here. We know that's 1 because this is a unit circle. So the trig function that we're going to use is the opposite over adjacent, and that is our tangent of x. So opposite h over adjacent, which is 1, equals tangent of x. So h is equal to tangent of x. So we can actually substitute tangent of x in for our height for the triangle. So 1/2 tangent of x. And this still really doesn't look like what we want it to. Well, let's see if we can manipulate it and see if we can get something familiar. So we know everything's multiplied by a half. We can actually multiply through by 2 and it doesn't change the inequality. So sine x is less than x, which is less than tangent of x. Now if we divide through by sine of x, we start to see something that looks really familiar. So divide sine of x by x and we get a 1. That's less than x over sine of x, which is less than tangent of x divided by sine of x. Okay, so tangent of x divided by sine of x. Let's do that over here. Tangent of x divided by sine of x. So tangent's equal to sine of x over cosine of x, and we divide by sine of x. Now really we flip the fraction and multiply, and that gives us 1 over cosine of x. So 1 over cosine of x. Now that looks familiar, except for it's the reciprocal. Let's look at what happens with our inequality signs when we take the reciprocal of something. So let's say we have 1/2 is less than 5, which is less than 10. And let's take the reciprocal. We know that 2 is going to be greater than 1/5, which is greater than 1/10. So when we take the reciprocal, it switches our inequalities. So 1 is greater than sine of x over x, which is greater than cosine of x. Now remember, we're taking this as x approaches 0. So we can take the limit as x approaches 0 of 1, which is on one side of sine x over x. And we know that that is 1. And we can also take the limit of cosine of x as x approaches 0. And that is also 1 as we get closer and closer to cosine. So we see sine of x over x is squished in between these two 1s. Now because of the squeeze theorem, we know that if it's in between two 1s, sine of x over x is also going to approach 1. So cosine of x goes towards 1. 1, of course, goes towards 1. So by the squeeze theorem, the limit of sine x over x as x approaches 0 is 1. Now we only showed this for the first quadrant. So in essence, really all we showed is that the limit of sine of x over x as x approaches 0 from the positive side equals 1. In order to really prove that this limit exists and is 1, we need to also show the limit of sine of x over x as x approaches 0 from the negative side also equals 1. Now you could do this two ways. We could take the absolute values and reprove this. We could also take a negative x and then prove it from that side. Either way will work, and I'll leave that to you as an exercise.